Okay, so now we're going to talk about absolute extrema. So we've talked about relative extrema, we've talked about concavity, increasing, decreasing. We've talked about all that facets of what are our big things for relative max and relative min. Well, now we have what's called absolute extrema. So for an absolute extrema, we want to let f be a function defined on some interval containing c. Then we know that f of c is the absolute max of f on the interval if f of x is less than or equal to f of c for all x in the interval. Otherwise, f of c is the absolute minimum of f on the interval if f of x is greater than or equal to all f of c for all x in the interval. So in other words, the absolute maximum is the largest possible y value, and the absolute minimum is the smallest possible y value. So instead of seeing the other notebook, we're going to draw it out so that we can see what's going on here. So basically what I'm saying is given any function, so say we have just a nice little cubic function here. If I defined a to be here, and say I defined b to be way out here. So what I'm saying is we have an endpoint here at A, we have an endpoint here at B. Our C, so this could be, say, C2, this could be C1. So our C values are our critical values. So we're going to have a process that's going to be an abbreviated piece of our relative max and relative min. So by creating this relative max and relative min, what we're basically saying here is one of these values, f of A, f of C1, f of C2, and f of B. Somewhere inside of here, one of these values is our absolute max and our absolute min, one of these values. We could have more than one absolute max and absolute min, but what that really means is they're the same y value and therefore could be multiple things there. So what does that tell us in terms of problems now? So we need some extra theorems in our process to really know what we're doing here. So the first one we have is our extreme value theorem. It says if f of x is continuous on AB, the closed interval AB, then f of x has both an absolute min and an absolute max on that interval. So this is a good theorem because it guarantees us that if it's continuous, I mean, we didn't pick up our pencil anywhere inside of that interval. As long as that's true, we're guaranteed to have an absolute max and an absolute min. If our function is not continuous in there, we can't guarantee that we're going to have either one of these values. So that brings us to how do we actually do this? So to find the absolute extremum, first step, just like when we did relative max and relative min, we're going to find all the critical numbers inside the closed interval AB. Next, we're going to evaluate each one of the critical numbers that we found that are in AB into the original function. We're then going to evaluate A and B. That's what I was talking about right here. F of A, F of C1, F of C2, F of B. Whichever one is the largest Y value, that's our absolute max. Whichever one is the smallest is our absolute minimum. So anytime that we have a polynomial function, we're guaranteed to have an absolute max and an absolute min. So first step here, f of x equals x cubed minus 6x squared plus 9x minus 8 on the interval from 0 to 5. So f prime of x is 3x squared minus 12x plus 9. We need to set this equal to 0 and solve for our critical numbers. So we can factor out a 3. You get 3 times x minus 3, x minus 1 equals 0. So we get x equals 3 and x equals 1. So now we come back up here and we look at this interval they gave us, 0 to 5. Well, both of our answers are inside of there. So we need to find the following. F of 0, f of 1, f of 3, and f of 5. And that's just going to get done by simply plugging in to the function that they gave us. So 0 cubed minus 6 times 0 squared plus 9 times 0 minus 8 gives us negative 8. Plugging in 1 cubed minus 6 times 1 squared plus 9 times 1 minus 8 gives us 1 minus 6 plus 9 minus 8. So we get 1, 2, we get negative 4. So plugging in 3 cubed minus 6 times 3 squared plus 9 times 3 minus 8 gives us 27 minus 54 plus 27 minus 8 gives us minus 8. Plugging in 5 cubed minus 6 times 5 squared plus 9 times 5 minus 8 gives us 125 minus 25 times 6 is 150 plus 45 minus 8 gives us negative 25 plus 20 minus 8 gives us 12. So this is going to be our absolute max. And in this case, both of these are the absolute minimums. We can have 2 absolute mins or 2 absolute max or how many ever, as long as they give us the same exact value. So same thing here. F prime of x is equal to, so in this case, we can have a product rule. So we'd have 1 times x minus 1 to the third plus x minus 3 times x minus 1 squared times 1. If we factor out the x minus 1 squared, we would have x minus 1 plus 3 times x minus 3. So x minus 1 squared times 4x minus 9 minus 10 equals 0. So x equals 1. And then x equals 10 over 4, which is 5 over 2. So in this case, we need f of negative 2. F of 1 is inside of that interval. 5 over 2 is the same as 2.5, which is also in that interval. And then f of 3. And we're going to plug these into the function they gave us, x minus 3 times x minus 1 all cubed. So we're going to have negative 2 minus 3 times negative 2 minus 1 cubed. So we get negative 5 times negative 3 to the third. So we get negative 5 times negative 27. So we get 135. Plugging in 1 minus 3, 1 minus 1 cubed gives us 0. Plugging in 5 over 2. So we get negative 1/2 times 5 halves minus gives us 3 halves to the third. So negative 1/2 times 27 over 8, which is negative 27 over 16. Plugging in 3, 3 minus 3 times 3 minus 1 to the third gives us 0. So in this case, this is our absolute max, and this is our absolute min. In a lot of cases, they will be the critical numbers that we plugged in, but we cannot always guarantee that. So always make sure that you work everything all the way out. So depending on what type of functions we're given, we could see other longer stuff here. So f prime of x equals low d high minus high d low over the bottom squared, which is x squared plus 1 minus 2x squared plus 2x all over x squared plus 1 all squared, which is minus x squared plus 2x plus 1 all over x squared plus 1 all squared. To make this a little bit easier, let's factor out a negative 1. With this, we could do the quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So this gives us 2 plus or minus the square root of 4 plus 4 all over 2, which is 2 plus or minus square root of 8 all over 2. Simplifying, we get 1 plus or minus root 2. Now, keep in mind that on this one, our interval was from 1 to 5. So we need f of 1 and f of 5 automatic. Now, square root of 2 is 1.4. So 1 minus 1.4 is not in that interval because that gives us a negative. So we only need 1 plus root 2. 1 minus root 2 is approximately negative 0.4, which is not in that interval. So that's why we only need 1 plus square root 2. So then coming back to our function over here, x minus 1. So x minus 1 over x squared plus 1 gives us 0. So x minus 1 over x squared plus 1 gives us 4 over 26, which is 2 over 23. 2 over 13, sorry. The last one, you get 1 plus square root of 2 minus 1 over 1 plus square root of 2 squared plus 1, which is equal to the square root of 2 over 1 plus 2 root 2 plus 2 plus 1, or square root of 2 over 4 plus 2 root 2. So we've got 0. So the question is, what is, so 2 divided by 13 is 0.15. And then second square root of 2 divided by 4 plus 2 times the square root of 2 is 0.207. So this is our absolute max. And 0 is our absolute min. So they can get ugly. Now, one thing to keep in mind is this right here is note that anytime that you're dealing with log of x, that log of x has a domain of x greater than 0, and e to the x has a domain of all x. So just make sure you remember that whenever you are working through some of these problems. Our log, so log of x plus a has a domain x plus a greater than 0, x greater than negative a would be the domain. So make sure that you remember that as well.